Hello, I am Anjali Datta, a research fellow in S.N. Bose National Center for Basic Sciences. I am doing my academic work under the supervision of Dr. Sunandan Gangobadhyay and Dr. Srimoy Ganguly. Today I want to share one of my previous academic work with you, and the title of my talk is Explicit Existence of Berry's Geometric Phase for Harmonic Oscillators in Non-Commutative Space. Our work is based on this recent publication. You can find easily from Google Scholar. So the outlines of my talk are like this. At first, there will be brief introduction about the definition of geometric phase. Then I will share a brief overview about geometric phase with you. Next, I will show you how a geometric phase of a generalized harmonic oscillator looks like because it is relevant to our work. Then I will try to explain what does a non-commutative space mean here. Then I will describe two types of periodic models that we will consider in non-commutative background, and I will show their geometric phase expression. Next, we calculate the geometric phase explicitly for those systems. Then at last there will be summarized version of our work, and I will mention the main findings of our work, and after the reference and acknowledgement section I will finish my talk. So what is a geometric phase? If a time-dependent Hamiltonian varies very gradually and periodically with respect to time, then the acquired phase factor by the eigenstate of that Hamiltonian may not depend on the time taken to complete the periodic cycle. Rather, it would depend on the geometric path traversed on the Hamiltonian parameter space. In this situation, the phase factor acquired by the eigenstate is called geometric phase. It was first discovered by the Indian scientist S. Pancharatnam in 1956, and later it is generalized by Sir M. V. Berry. That's why it's also referred as Berry's geometric phase. Let us visualize this matter very briefly. Let us first think about the time-independent Schrodinger equation. The eigenstate of such equation can carry a phase factor with it, and this phase factor is completely dynamic. That means it is a time-dependent function, and this dynamic phase factor does not affect the probability amplitude at all. The expression of such dynamical phase factor is this, and the energy is totally constant here. That means energy is time-independent quantity, as the equation is time-independent. Now look at the time-dependent Schrodinger equation. Here also dynamical phase can be considered along the eigenstate, and its expression is just modified as the energy is time-dependent quantity now. Now let us assume that the time-dependent Hamiltonian is varying very slowly with respect to time. Then we may approximate its first derivative to be 0. If we want to investigate the effect of this approximation in that system, we find out that the eigenstate is carrying a phase factor like this. Next, we reveal some time-dependent parameters for which the Hamiltonian is varying with time. There are some R1t, R2t and so on. If we expand this psi dot t with respect to this set of parameters R and put it again inside the previous phase expression, we see that this phase can be represented in these parameters R. If we make this whole system periodic as if the Hamiltonian completes a cycle on parameter space R, then this phase is no more time dependent, rather it depends on the path traversed on parameter space. So this is an expression of geometric phase now. There are so many examples of time-dependent models available in literature where their Berry phase form can be found out. As we intend to proceed with harmonic oscillator, I just show you the Berry phase expression of a generalized harmonic oscillator. So this is the Hamiltonian of generalized harmonic oscillator, generalized because the scale invariant term in the right side is added as a third term with the Hamiltonian of a harmonic oscillator. Now such kind of scale invariant term can arise due to many different physical reasons. For an example, if a background field interacts with a harmonic oscillator, then such kind of scale invariant term arises in the corresponding Hamiltonian. Now the interesting thing is that if such kind of term exists in the Hamiltonian of harmonic oscillator, then the corresponding time dependent coefficient dt directly contributes to form a structure of Berry phase. If we look at its Berry phase form, we can easily realize that without dt, which is a coefficient of scale invariant term, the geometric phase is 0. Now we are not going into the details of the constructing procedure of this expression. We just know this result, observe its structure, and we'll use it in our own purpose. Let's proceed. As we want to carry on our work in non-commutative background, I just briefly want to make clear what the non-commutative space means here. We already know that quantum mechanics is non-commutative because the commutation relations between position and momentum operators is not zero. But in ordinary quantum mechanics, the commutation relations among the position operators are zero, and the same thing happens for the momentum operators also. Here, in our purpose, non-commutative space refers that all the commutation relations are non-zero, and the non-zero values of these commutation relations will differ according to the structural form of non-commutative space. Here we should mention another point that in our purpose we will consider time dependent non-commutative space. That means the commutation relations satisfied by the operators are not only non-zero but also varies with respect to time. Now I want to discuss briefly what I am planning to do. At first, we consider one kind of time dependent non-commutative space, say type 1. And in this type 1 non-commutative space, we set up a time dependent generalized harmonic oscillator, which we showed in previous slide that it already has explicit scale invariant term in its Hamiltonian, which can form a Berry phase. Then in another kind of non-commutative space, say as type 2, we consider just a time dependent harmonic oscillator which has no scale invariant term in the original Hamiltonian, but the term will arise after shifting the variables from non-commutative space to commutative space. That means here only the non-commutative space will be responsible to construct the Berry phase, unlike the first case. Here it differs from the first system. Then we will study the geometric phases for both systems explicitly. Now I am going to describe which periodic models are to be considered in non-commutative background. This is the first system, and this is the original Hamiltonian with scale invariant term, and this is the structure of non-commutative space. For shifting the variables from non-commutative space to commutative space, this is the required Bob-shift relations. And finally, the Hamiltonian in terms of commutative variables is this, where the time dependent coefficients are the function of non-commutative parameters now. And we clearly visualize that in the absence of non-commutative space, the factor dt, which is necessary to form a Berry phase, does not vanish. This is because the scale invariant term was already included in the original Hamiltonian. Here is the second system. This is the Hamiltonian of time dependent harmonic oscillator. Here is no scale invariant term, and this is the non-commutative space structure. Such kind of non-commutative space is recently introduced in literature. You can find the corresponding reference from reference section at last. After variables shifting, this is the form of later Hamiltonian, where the time dependent coefficients are also function of non-commutative parameters. But in the absence of non-commutative space, the coefficient of scale invariant term vanishes. That means the Berry phase completely belongs to non-commutativity for this system. According to this system, if the non-commutative parameters are non-zero, then Berry phase should exist. Now the generic form of Berry phase structure for both systems are here. It is same. But we should always remember that the difference is hidden inside these time dependent parameters, what we have discussed earlier. Now we are going to verify the explicit existence of this phase for both the systems. We will just show a single example for each system, as these are enough to draw the main conclusions of our work. This is the example for first system where non-commutativity was not necessary to form a geometric phase. Here we set the original Hamiltonian parameters Pt, Qt, Rt as constants and set the non-commutative parameters to vary sinusoidally. Interestingly, the phase is revealed out as 0. So, these certain choices of non-commutative parameters show that in spite of existence of scale invariant term in Hamiltonian, geometric phase may be 0. Let's go to the next example. This is the example of second system where non-commutativity is necessary to form a geometric phase. That means, according to the structure of this model system, geometric phase should exist when the non-commutative parameters are non-zero. Let us verify it. Like the previous case, we also set the coefficient of the original Hamiltonian as constant and the non-commutative parameters are non-zero periodic function of time. Still, the phase is found out as 0. So, in a summarized version, what have we wanted to do here? We basically investigated whether a non-zero geometric phase is picked up by a periodic system. In this regard, we considered two different kinds of periodic system in two different kinds of non-commutative space. While the first system has an explicit scale invariant term which is necessary to obtain an expression of Berry phase, the second system does not contain so. Rather, a scale invariant term arises in second system when the corresponding system is mapped in terms of standard commutative variables. Then a generalized expression for Berry phase is obtained for both the system. Next, explicit value for Berry phase is obtained for the two systems under various conditions. Interestingly, for both the systems, for certain choices of periodic parameters, the geometric phase vanishes. It happens even in the presence of non-zero non-commutative parameters, which was an essential condition to generate an expression of Berry phase for system 2. So what are the main findings in our work? Our study clearly indicates that the existence of scale invariant term in the Hamiltonian is an essential but not sufficient condition for the existence of a non-zero geometric phase. Rather, the periodic Hamiltonian has to be designed extremely carefully in order to ensure the existence of a finite non-zero value of Berry phase. This is one of the main findings in this work. Here are the reference and thank you all for listening my talk.